one right now. So. Just go double check, make sure it's using right. Are there any questions that you want me to address, based on the material on Monday? Because we went through, really kind of, this is the first time I ran through an actual example and illustrate, how the substitution, takes place. So it's actually a pretty good example from my perspective. But you guys can tell me whether, that's sufficient as an example, or whether you have any questions about the example itself. Yep.
So first, probably in the text. So what does it mean by fire for the last three bullet points?
Okay, so we can go over that, when we are at noontime. Yeah, so we can talk about that. Yep.
Example, I was wondering if you could break down the definition, I guess, of inference. There was three bullet points where in notes. It was like I think two existential statements.
Okay, I see. Okay, I see.
I was wondering if you could break that.
You mean this part here?
Yeah.
Okay, yeah, I can talk about that. All right, so I got two questions kind of queued up. That's and I went back to the recording on Monday. I actually spent 22 minutes talking about ChatGPT. Yeah, definitely not my idea of, one can say that we are creating artificial intelligence in our own image.
Especially with ChatGPT.
Yes. And I question that. I question the wisdom of that.
There's certainly good aspects and bad aspects, but ChatGPT seems to be grabbing a lot of bad aspects, like lack of logic.
Yeah, but it's also, spinning up a lot of quote unquote competition, who want to do about the same thing.
Right.
Yeah. All right, I think it's noontime already, so let's go ahead and get started. So about the firing of the rules and how it works. So the first thing we want to do is to reestablish what is the set W. The set W is basically the set of all the well-formed formulae based on what we define in alpha and also what we define in omega. So those two alone, okay, can quote unquote span W, which is the space of well-formed formulae. So are we good with that concept? We have a space of well-formed formulae. Basically, they're equivalent to expressions that are syntactically correct. Are they meaningful? Maybe not. Are they useful? Maybe not. But are they syntactically correct? Yes. So we're good with the set W. Then we move on to the set of D. So the set of D is a set of WFFs that are quote unquote derivable from the WFFs in iota. So they are well-formed formulae, which means D has to be a subset of W, but at the same time, I has to be a subset of D because the well-formed formulae in iota is given to be true to begin with. So they are quote unquote derivable, but it takes no steps in order to quote unquote derive. So are we doing okay so far with the concept of the iota set, which is basically the set of all the expressions that are known to be true, okay? Don't ask me why, they're just given to you and they are true to begin with. Then we have D, that are quote unquote derivable, which means you're starting with iota. These are the expressions that we can show that they have to be true. If everything in iota is true, then everything in D also has to be true. But they're not given to you, then you have to kind of work to derive those particular expressions. And then everything in D is also in W, because W is just the entire space of all the possible expressions, derivable or other. So is that okay so far? All right. Okay, Tyler, I got a question for you. Did you take the test at the DSPS center?
Yeah, right.
What happened to the test? Because I never received it.
It was online.
It was on paper. You turn it into the DSPS test center?
Yeah, I'll be on.
Huh?
I'll be on.
But I never received anything for grading purposes. So do you want me to check with the DSPS center or do you want to go check with them? Not now, I mean, at some point, because huh? Okay, I can do that, but until I get the test, I cannot grade it. Yeah. I believe I checked the markup, you're supposed to grade it back to me in a sealed envelope.
Oh, I think back to this.
You took it on Wednesday?
No.
You took it on Thursday. Yes. You brought it back to the department, the division office, and then they can put it into my mailbox. Do you have it? Okay. So I'll count on you to do it now, okay? All right. So getting back to this stuff here. All right, so now what we want to do is to talk about, how do we make use of the transformations? Those are the elements of the set that we call zeta or z, if you will. So now what we want to do is we assume that we have three Greek symbols, theta, phi, and psi, and they're elements of alpha, which means we are allowed to use these placeholders. Each element E of Z has the following format. In other words, each transformation rule has this format. On the left-hand side, we have M, which is a set of WFFs that refer to the Greek symbols. And then on the right-hand side of this inferred symbol, we have WFFQ, which is some kind of WFF using the same Greek symbols, which will be theta, phi, and also psi. Is that okay? Because right now, at this point, we are really just defining the terms and describing what each element of zeta is going to look like. Okay. Are we still doing okay so far at this point? Because if we're not doing okay, then the further discussion is not. All right. We do not seem to have any questions. So now we want to use this vocabulary that we have established up here to determine when we can fire a transformation rule and what happens when we do fire a transformation rule. So we have an if then here. So the if has a bunch of conditions. So the first condition or the first bunch of condition is there exists A, B, C in W. So remember, W is the set of all the well-formed formulae. So A, B, and C are really just well-formed formulae. They don't have to be derivable. They just have to be well-formed. And then we can also find a T, which is a transformation rule in zeta. Okay, so now we have a few things that we have selected a bunch of stuff from W and one particular thing from Z. And we want T to look like this, okay? So T as a transformation rule is gonna have a set M on the left-hand side of the infer symbol, and it's gonna have some kind of WFF involving the use of the three Greek letters, theta, phi, and psi on the right-hand side of the infer symbol. So right now, I'm just describing all the ingredients on a little tray. I haven't decided yet whether I can do something with those things in the tray. I'm just describing what I'm collecting on the tray so that I can decide, can I do this, in the end. So the last one is the most important one. The last one looks really confusing because the first part here says for all WFF, some WFF involving the three Greek letters, theta, phi, psi in M. Okay, so let's stop right here. Okay, let's pause right here. Because M is the left-hand side of a particular transformation rule in Z. So that means it can be empty. Okay, occasionally we can have a transformation rule where M on the left-hand side is empty, but most of the time it's not empty. So when it's not empty, it has multiple elements. So I'm basically saying each element is going to look like a well-formed formula involving the Greek letters. Is that okay? So what are we going to do with that one? Well, for each one of those, we want to find the same well-formed formula, the same structure applied to ABC, which are elements of the set of well-formed formulae in E. So those are already derived. Okay, so this part here by itself is probably the most important part, but it can also be the most confusing part. So do we have any questions about this part?
So the third bullet point, so
Which one? The third one, this one?
T equals M implies dual transformally.
No, it's not implied. It's inferred. So I'm really just describing the transformation rule that I'm taking a look at. Okay, so in other words, everything for the first 3 points here, I am just going to the set W and say, okay, I'm going to grab these 3 things here. And then I move on to go to the set zeta, and I grab one single transformation rule that I call T and go, okay, I'll put it on my tray too. The third one is really just to take a closer look at the transformation rule and break it up into 2 parts. The left-hand side is a set M, and then the right-hand side of the inferred symbol is WFFQ, theta, phi, psi, which is basically a particular well-formed formula that appears on the right-hand side of the inferred symbol. I just call it WFFQ so that I can differentiate it from other well-formed formulae. Is that okay? So the first 3 points are really just grabbing things into my tray, labeling each thing, and say, you're M, you're T, you're A, B, C. Okay? That's all I'm trying to do. I'm just labeling those things. I haven't even decided yet, can we actually do this? Nope, I haven't decided yet. The 4th point determines whether we can actually use the rule to make something out of the things on that tray. Are we doing okay so far with the first 3 bullet points? Okay. So the 4th bullet point is the confusing one, because what we're doing now is to say, let's focus on the left-hand side of the transformation rule that I have chosen out of that. Okay, it is a set, so it has multiple elements. Each element is a well-formed formula, right? And all the zetas can make use of the Greek symbols. So I'm basically just using WFF, theta, phi, psi to describe each element that I can find in M, which in return is the left-hand side of a transformation rule. Is that okay? I'm just focusing on one element on the left-hand side of the transformation rule T that I have just randomly chosen from zeta. Is that okay? So what do I want from it, right? What do I want from this particular well-formed formula? I want to preserve the well-formed formula with all the ands, all the ors, all the nots, and so on and so forth in a particular structure, I want to preserve that structure. But wherever theta is, I'm going to replace it with A. Wherever phi is, I want to replace it with B. And wherever psi is, I want to replace it with C. That is the most important part. I'm trying to do substitution. The Greek letters are basically placeholders. A, B, and C are representing actual well-formed formulae that I can find in W. So I'm picking something that can be really gigantic, complex as A, and go like, okay, you're going to go to all those spots where theta appears in this particular well-formed formula. I'm going to look at B, which can be another huge, big, complex, syntactically correct expression, and go, you are going to all the spots where phi appears in this well-formed formula. And then the same thing with C with respect to psi. Is that okay? So all I'm doing is to do substitution. Okay, so after the substitution, WFF, which is the structure of an expression, but using A, B, and C as its components, is going to be a well-formed formula anyway, right? Because A, B, and C are well-formed, and we know, since the name is WFF, it is also well-formed. So now I have a new expression, okay, which is WFF of A, B, and C, and I'm asking, is this well-formed formula in D, the set D? So if it is in D, it means it's already derived. Is that okay? And if it is already derived, then I have this particular one has passed that test. And I'm going to do exactly the same thing to every single element in the set M, which is the left-hand side of the transformation rule. If all of them pass the test, okay, then the quantified expression is going to be true. So now we have all 4 bullet points being true. I can find A, B, and C from W. I can find T in C. T looks like this, and we can apply that rule because the left-hand side has all the matches to something that's already derived in D. Is that okay? Those 4 things are important because now I look at all the things in my tray and I go like, okay, now I can make something new. Okay, I grab A, B, and C, and then I also grab WFFQ, which is the right-hand side of the inference, and say, I'm going to take A and put it into all the spots of theta of WFFQ. I will take B, put it into all the spots where phi appears. I'm going to take C and put it into all the spots where psi appears. Then I have a new well-formed formula, which is known as WFFQ, applied using A, B, and C as parameters. That is just a well-formed formula. It belongs to W anyway. But now I can also say it belongs in E because I just derived it. And that is what it means when I quote unquote fire a transformation rule, is to confirm whether a particular well-formed formula is an element of D. Are we doing okay with that concept? Okay. I know it is a little bit on the abstract side, but that's basically what programs are. I mean, programs are really abstraction of what we want to do, and we probably know how to do that by hand, but you have to do the abstraction to get it done. So this particular thing, okay, this entire, if blah, 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 then go ahead and fire the rule. The example on Tuesday is intended to show exactly that. So that means if you look at the example here, we start with iota with these things, right? And then we start with alpha with these things. We start with omega with these things. So I think we determine what can be in W. Everything in alpha is automatically in W. P and P is also in W because P is in W, and the conjunction operator requires 2 operands. So if we supply 2 well-formed formulae to the conjunction operator, then the expression is also going to be well-formed. So we determine that P and P is also in W, P and P is also in W, and so on. So we can have a lot of stuff that is not useful at all in W, but they are syntactically correct. Okay, so that's the example. And then we also know that P and Q implies S or T is ordered in W because, oh, thank you. That is very helpful. Okay. All right, so yes. So now we know a whole bunch of stuff is in W, they are well formed. But just being well formed or syntactically correct is not what we are interested in, because what we are interested in is whether a particular well formed formula is derivable or not when we're trying to prove a theorem. Is that okay? All right. So now we try to determine what is in D, what is derivable. P implies Q is derivable because guess what? It is in iota to begin with. Everything in iota is also in D. That's a given. All right. Q implies R is in D. Same thing. It is in iota as well. And then we have P and S in D because that's also in iota. We do okay so far up to this point here. Just a basic membership of who is in W and who's in D and so on.
So these are the first two words.
Well, these are the quickest one. These are the easiest one to determine whether they are elements of Q or not because they're in iota. All right. So now we gather things onto our tray. Okay. So I try to map the terminology here back to the terminology in here. Okay. But we're going to focus on the concrete example. So what I'm doing here is using the A, B, and C. I am choosing P to be E. I'm choosing S to be C as variables in the previous description. And I'm basically saying, hey, everywhere the theta appears, I want to replace it with P. Everywhere the psi appears, I want to replace that with S. Let's see what happens, right? So it turns out that if I did that, then the expression phi and psi becomes P and S. Does that make sense? Okay, then you just gonna pause here. I'm just doing substitution here. Okay, so yes, okay, fine. What is the big deal? Okay, if phi is indeed just P as an expression, and then psi is indeed S as an expression, yes, that thing is in D. So what is the big deal? Well, the big deal is this is the only expression in M. Okay, remember the set M, which is representing what is on the left-hand side of a transformation rule. This is the only expression in that entire M. So that means, oh, okay, so we have satisfied all the requirements to quote unquote fire the transformation. Yeah.
So why is hindsight infers phi? Why is hindsight?
Well, we can have the other one to do the commutative property, but in this case, I'm only focusing on one side.
Just optional. We can choose whatever.
Correct. Yeah, you can have another, if you want commutative property of being commutative to be in the system, then you would have another one that says psi or phi, and then infers here, in that case, psi. But the other way around. You would have the same thing here, the same pattern, which is phi and psi, but it would say infer psi instead of phi. In order to kind of catch the commutative property of conjunction. But in this case, this suffices. So I don't want to complicate the system more than it needs to. So as a result of firing this rule, then we say, hey, what did we use again for phi? Oh, we were using P to take the place of phi. And the inference, when we fire the rule, we're basically saying whatever we used for phi by itself, in this case, would also become quote unquote derivable. And we now confirm that P is also an element of D. Okay, so what elements are in D is constant. Okay, it is already predetermined, it is static. The only question is, when do we confirm that something is in D? That becomes the procedural. Are we doing okay so far? Okay. So the second rule is kind of the same thing, okay? We have three cases of firing these rules. So the second one is to say, okay, let's reach into the W set, right? I'm grabbing P, I'm grabbing Q, and I'm grabbing R as the three things that I took out of the set of W. They're just well formed. Are they derivable? Maybe, maybe not. We don't care. Okay, we just need those to be well formed. And then we chose this rule from Zeta, and then we say, okay, let's do some substitution here. Every place I see phi, I want to replace it with P. Every place I see psi, I want to replace it with Q. Every place I see rho, I want to replace that with R. And then I want to see, do I get all the matches with every single element in M? Are we getting the matches? So now, when I say are we getting the matches, I'm asking, are those expressions in D? Question, yes.
So are you getting, you know, the equation that you're firing, are you getting that from iota or are you getting that from zeta?
Okay,
Because
so which set is which set? What is the set iota contain? You're having a type mismatch here. So what is in the set? Which one again? Iota, right? You're trying to determine between iota and zeta. The kind of elements are different. What do we have in iota? What kind of stuff is in iota?
Things well-formed formulae and are true or known to be true.
They have to be well-formed formulae. So we don't know whether they're true or not. Well, okay, everything is in iota is assumed to be true, but more importantly, in this discussion, they are well-formed expressions or well-formed formulae. All right. Okay, so that's the type of elements in iota. What kind of stuff is in zeta? In zeta?
transformation.
Transformations. Now, what does a transformation look like? In general, what are the things that we can find in a transformation? It has a left-hand side and a right-hand side, and in the middle we have an operator, right? The operator that looks like a T that is rotated like this is called inverse. Okay, the left-hand side of the infer or the inference is a set of well-formed formulae using the Greek symbols. On the right-hand side, we have a well-formed formula, a single one, using the same Greek letters. That's the format of an element in Zeta. So to go back to your question, this is the long way of answering your question. Zeta has all the transformations. So if we are choosing, if we're getting a transformation, we have to be getting it from Zeta.
So if we didn't know zeta,
Then you cannot do a single thing. Zeta is really the most, well, I shouldn't say most important, but it really is the most, it's the one part of the entire system that gives it the dynamic nature of what we can do with the system. Yes.
You know an example where it's not.
It's not indeed. Well, that's actually a problem because now we are asking, can we find that needle in a haystack? And the potential answer is no, we may not have this needle in the haystack. So if the haystack is finite, it's not a problem. You just need time, right? Go through every single cubic inch of the haystack, and eventually you can confirm whether the needle is in the haystack or not. The problem is the haystack is infinitely large now. In other words, W as a set is infinitely large. So by using these derivations, we can confirm what is in D and what is, but we cannot really rule out things not to be in D. We cannot say what cannot be in D. We can only confirm what is in D. So, and because W is infinitely large, that means you never really know. Maybe the next derivation will find that needle, maybe not. Okay, so later on we'll find something that can help us with this problem. Yep.
And in the last three bullet points, we're just trying to determine whether certain rules are indeed essentially, right? Like you say,
The rules are not in D, the rules are all in Zeta. but we want to know whether certain expressions are in D or not. In this case, the one that we're really interested in is just R. Can we make a conclusion that R has to be true if everything in iota is true to begin with? And the answer is yes, we can actually prove it using the transformations. So that's basically more or less a kind of like a expanded explanation of what we talked about on Tuesday. So combining the lecture up to this point, which is about 12:30, and the lecture that we did have on on Monday, hopefully that will help you kind of get a better understanding and have more traction with what it means when we say, oh, we can fire one of those rules and end up labeling one of the expressions in W to be also in D because it is now known to be derivable. Yep.
So these last 3 bullet points are straight from Zeta, right? There's nothing
Yes.
in there.
Yep. And the first one makes use of the last rule in Zeta, and then this one makes use of this one in Zeta, and then this one makes use of this one in Zeta.
So D, it consists of iota and substituting Greek letters for their normal letters, and then firing them through.
If you can fire. In other words, you have to meet all the requirements specified by the left-hand side of the index. It's a pattern matching thing. Okay, can we match those patterns? If the answer is yes, we can find something and match all the patterns specified on the left-hand side of the inference. Then we apply the rule, which then use all those substitutions applied to the well-formed formula on the right-hand side, so that the substituted version of the well-formed formula on the right-hand side can now be confirmed to be in D, which means it is derivable.
So using these 3 rules, we can really confirm everything in alpha and in D. We can just like make some changes.
No. This is only confirming that R is in D.
We can change it and make Q in D too.
The way we set up thing right now, yes, Q is in D, but that's because of the previous step. Let's see, Q is in D. We know Q is in D because we can just use this rule. We can use the same rule here and apply that to P implies Q, and also P by this time is also in D already, so we can actually confirm Q is in D.
So now iota is limiting us what we can just use.
No,
They don't have Q and R there.
well, we know nothing about T, so we can never confirm T is in D. Because there's nothing here that mentions T at all. So even though T is a variable in alpha, there's nothing in iota and zeta that can help us label T as a well-formed formula to be derivable. Is that okay? So T cannot be confirmed to be derivable in this case. I mean, it's doing okay so far in terms of the mechanism of how propositional logic works.
But we can have 5 for T. Just as we did in the third from last, we said 5 for 3. We can say 5 for T.
No, yes, you can, but then the rule cannot fire because you cannot match the pattern. Okay, so think about this. Okay, let's make T one of the Greek letters. Okay, it doesn't even matter which one. But when you look at the left-hand side of every single transformation rule, it has to involve an expression involving T itself once you have done the substitution. So you look at iota, you look at everything that is confirmed in D already at this point, nothing mentions T at all. So we know for sure that if you have an expression that has T in it, we cannot fire. We cannot fire the transformation because there's nothing derivable up to this point that contains T in it. Is that making any sense? I think what your question is you're not understanding what the fourth point is about. Because you would have failed the fourth point if either one A, B, or C is T. In our specific example here. Yes, go ahead.
So just to clarify, so in this prompt, you would ask if T is an element, if T is true, we haven't, there's no way to
We cannot confirm it.
confirm it. Okay.
So the idea of the propositional logic is to derive a rule from a set of symbols and operators.
So the rules are usually given to you. In other words, you're using the rules that are given to you, and all you're doing is doing pattern matching so that you're trying to understand, what is derivable. Hopefully, the one thing that you want to prove is also derivable. But the problem is we cannot know, confirm for sure whether something is not indeed.
Is phi and psi, does that have to be PNS specifically?
No, it's only a matter of you can choose whatever in W to be the Greek letters. The question is, as a result of that choice, can you fire the transformation rule?
So if we were to substitute PNS and chose two different random values like R and T,
Yes.
then we would say that R is.
Then can you find a pattern? Can you find these expressions to be in D already? That is the question. Okay, let's use a concrete example. Okay, so let's say phi is R, psi is T, and then rho is R. Okay, so we have STR. Okay, STR. Okay, so now we are looking for something in D that has S implies T. So do we have that? Do we have S implies T already being marked as derivable? Nope.
Because it's not.
We have not confirmed it, okay? So we can't fire the rule because we cannot find something in D that matches the pattern of S implies T. And we need that match for everything on the left-hand side of the inference. Yes,
So so say we're trying to find T, does T have to be an iota in order to find it? Because that's where we get all the elements of T in the first place, right?
so typically, yes. So if you want your T to be the theorem, in other words, you want to know whether T itself is derivable, you probably need iota to contain expressions involving T in some way. Because otherwise, we have no way to relate T as a variable to the rest of the variables. Unless, yes, don't you like it when I say unless, okay? So there are two things I use a lot when people ask me questions or when I answer questions. One is unless, and then the other one is it depends. So the unless in this case is unless your question is whether T or not T as an expression is derivable or not. Because in that case, we can use the empty set thing here, because then you can just say, okay, let's make this phi T. And then the left-hand side basically has no constraint. It doesn't say anything. It's like everything goes, let's go find the rule. Whatever you choose as your phi, let's go ahead and find the rule. So now we can just automatically mark T or not T to be derivable.
But there's no phi or not phi in the set of zeros on the left side.
It's,
Make use of that.
it's okay. So we are talking about this particular rule, right?
Yeah.
This particular one. So that means, there's no actual constraints. There's no pattern that you need to match. You can pick phi to be anything you want, and then we can just immediately fire the rule because, it is by default, the left-hand side is by default saying everything goes. Pick whatever you want to be your phi, and if you want phi to be T, fine, no problem. Fire the transformation, and now we suddenly mark T or not T as a well-formed formula to also to be derivable.
But isn't that useless because you can't, there's no other Z
Yes, it is useless.
transformation, okay.
Yes, you can mark a whole lot of well-formed formulae to be derivable, but most of the time it does not relate to really want in the end. Yes,
How would you use the first transformation? Because it's
the
a
first
set,
transformation.
yeah, it's a set on the left.
So in this case, it's not really particularly useful, but if you have other things that relies on conjunction, then that formulates the conjunction expressions that may be necessary for yet other transformations to take place.
So if you have like two elements, phi and psi, then phi and psi is in the
Yes.
up.
Yep. Which doesn't say much, right? Because it's just kind of default, because everything in D is already known to be true. So if they're already if each one is known to be true, the conjunction of those have to be true anyway. But it does make preparation in case you have other derivation. So if I code in, let's say, De Morgan's law, okay, which one of the De Morgan's law involves your conjunction. So if I put in De Morgan's law, then this can become useful because now I have a factory of creating conjunction expressions. So I can use those conjunction expressions to feed the transformation rule representing De Morgan's law. But I don't have De Morgan's law here, so it's not very useful. All right, so are we doing okay so far?
Another example.
Well, maybe I would kind of move ahead and then we can come back and do an example after I make my point, okay? Because you guys may not be interested in another example anymore. After I make my point. All right, so the point that I'm making here is, well, there's one example here, but we're gonna skip that too. All right, so we talk about completeness and soundness. We can talk about that later too. So we're skipping all the way to resolution because I want to give you an overview of concepts right now. So to get an overview, resolution is an important thing. So I'm going to use linear algebra, not linear algebra, Boolean algebra to do the derivation. So we'll take a quick look here and find out, how Boolean algebra works. I have not formally introduced the Boolean algebra, but it is an algebra. It is just a little weird sometimes compared to what you already know about regular algebra. Okay, so the first thing I do here is to transform the implication into the negation of whatever is on its left-hand side, which is the entire conjunction, or the right-hand side. That is one way to define the implication. And if people are thinking, I don't remember you talking about it, then I would refer you back to the video of the first week of the entire semester, because we did talk about it in the first week of the semester. Okay, A implies B is exactly the same thing as not A or B. That is one way to define the implication. So I'm just getting rid of the implication here. So I negate the entire left-hand side, and then put an or here of the right-hand side. So in here, I am using the implicit priority of operator of conjunction having the highest priority. But okay, I take it back. Negation has the highest priority. Conjunction has the next to the highest priority. Disjunction has the next one, and then implication has the lowest priority. Okay, so those are kind of implied. All right, so down here, I'm using associative law because when you have an or and then it's oring something which is itself, it's an or as well, then the parentheses can dissolve because it's just like when you have 1 plus in parentheses 2 plus 2. The parentheses around 2 plus 2 is useless, okay? Because addition itself is quote unquote associative. So we still remember all those rules? I know the names may not be easy to remember, but I'll be remembering the concept of associative, okay? Because that's kind of important. The next one is kind of odd. It looks a little odd. But before we get to that one, let's go ahead and take we'll take a short break here. You're right. This time I do have the QR code, but I need to make it, give me a second here. I need to. So the word for row taking is B dash, which is the LaTeX symbol name for that, rotated T symbol. And let me say publish, and that would also give me the QR code. I'm not sure how much of the QR code is actually needed, because QR code by design have redundancy. So you don't really need the entire. Yep. B dash. It's V dash, VDASH, all lowercase. Coincidentally, just 2 days ago, I received a note from UC Davis asking me whether I want to publish my dissertation so that it becomes Creative Commons. Okay, so it has a Creative Commons license. And I say yes, and then they almost immediately reply with a link to it, because they already have it completely digitized. They just needed my okay to release it. And I was looking through my own dissertation and was like, what kind of person would write derivations like that? All right, so are we good with the row taking activity? Are we all done here? All right. So getting back to the note here, okay, so we're doing the derivation. So from the third line to the fourth line, the change is whatever is just phi over here becomes phi and true. So now the question is, can we do that? Well, as it turns out, true is the identity of conjunction, just like 1 is the identity of multiplication. In other words, if you have x in the multiplication, if you just say x times 1, people may ask you why bother, but they cannot say that you're wrong. Okay, are we doing okay so far with that? All right, so we do the same thing with row. So row becomes row and true. And then over here, this true becomes psi or not psi. Are we okay with that concept too? True is the same thing as whatever and the negation of that whatever. Yeah, okay. In this case, I just chose to use the psi and psi or not psi to take the place of true. Are we good so far? Now, yes, the sanity, you can question the sanity of this derivation, but the correctness of the derivation cannot be questioned because it is step by step. In other words, you can question, why am I making the thing more complicated from something that's simpler from before, but you cannot say that it is wrong. Are we doing okay so far with the derivation? Okay, so the next step is distribution. So if you look at a conjunction like multiplication and you look at the disjunction as an addition, you can do distribution here. And we can do exactly the same kind of distribution in Boolean algebra. So we are distributing the disjunction over the conjunction. So now we have phi and psi, not psi, and then we have phi and psi over here. I changed the order as well as I distribute. The reason why I can change the order has to do with, in this case, disjunction is commutative. So when we have commutative, it means you can swap the two sides of an operator. It does not change the output. And I do the same thing with row. So we have row and not psi on as one thing, and then we have row and psi as the other thing. All right, so I just made the original thing, which is relatively simple, into something that's much longer. So now we go the opposite direction. We start to do some simplifications. So the first simplification going from here to here is absorption of some kind. And let me see what we are doing here. Oh, right, on this side here, we have, oh, okay, I see what I'm doing here. So we have, this is the opposite of distribution, also known as factoring, okay? So what am I factoring? I am looking at this not phi and not psi. And then I'm also looking at the phi and not psi, which is this one. So I'm looking at the first item here, the third item here. And then I use factoring and say, hey, they are all both ending a not psi. So we'll just combine the first part into its own disjunction. And then that disjunction is ended or conjunction using a conjunction and joined with a not psi. Okay, are we doing okay with that one? If you look at, and as multiplication and you look at, or as addition, this is basically the same thing as what you normally do, with factoring. Is that okay? All right. And then from this one to this one here, and I do another factoring, which is combining this, psi and not rho. And I combine that with this. The next one here, yep, combining it with this psi and rho. So using factoring, psi is the common one, so it's separated out. And then the differences would be just not rho in one is appearing here. And then we have rho by itself, appearing here. So once again, it's just factoring. So by factoring, we combine these two. But once we do the factoring, we recognize that we can do some really interesting simplifications. Because now we end up with not phi over phi, which is true, exactly. And then on the other hand, we have rho or not rho, same deal, it becomes just true. So the next one here, that's why we have this true here, replacing not phi or phi. We have this one or true here, replacing rho or not rho. And then once we have that simplification, we also simplify the one and out of this whole thing, because one and whatever is just whatever. So let's not, make it more complicated than it has to be. So we just have not psi left. This one here, same deal, okay? Psi and one is really just psi. So we just simplify that to psi all by itself. And then now we look at these two and we go like, not psi or psi is really just true. Okay? And now we have true or blah, blah, blah. If we have true to begin with in a disjunction, the disjunction is guaranteed to be true. Okay, wait, hold on a second here. Remember, you guys, I told you that whenever I claim something, you have to go like, okay, is that really the case? Can I prove that? So the question is, can you prove it? Can I say, if you have a disjunction, remember this is just a longer disjunction because each component is part of a disjunction. If one of the components of a disjunction is true, then the whole thing is true already. How do we prove that? Truth table, very good, okay? So, if you cannot remember how to prove stuff like that, I would jot down a little note, and say, okay, use this as an opportunity to exercise and try to use a truth table to prove that one or whatever is just one. Okay, because those are little exercises that you can do in order to strengthen not just your understanding of the material, but also your skills. How quickly can you apply what you learned already? It comes from these little exercises. We doing okay so far? So what is the big deal? This long derivation here, blah, 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 just ends up to be true. What is the big deal here? And actually, what is this true applied to? What is being true here? Are we saying that phi is always true? No. Yes, go ahead. It's the implication, very good. So this true here is applied to the implication. The implication is always true when the two sides of the implication follow a particular pattern. So once again, we are going back to patterns, okay? This pattern here guarantees, okay, on the left-hand side, it guarantees the right-hand side. If you start with this pattern, you always end up with this pattern here. It always implies the other side is true. Okay, so what is the big deal? The big deal is on the left-hand side of the implication, how many Greek letters, how many distinct Greek letters are we using? 3 of them, right? How about on the right-hand side of the implication? 2, okay? So this is a big deal because we started off with 3 variables, 3 letters, and we only ended with 2. So if we repeat application of something like this, hopefully, eventually, we'll end up with 1 or none, which is kind of the objective. Is that okay? So this is called resolution. This implication here is called resolution. Whenever you see a pattern like this on the left-hand side of the implication, where the most important part here is psi. Now, psi itself doesn't have to be a single variable. It can be a big, huge, small expression. Whatever it is, does not matter. Because we just need one disjunction to contain psi. We have another disjunction here to contain the negation of psi. And then these 2 disjunctions are ended together. That's the pattern that we're looking for. If we can find that pattern, and it is true to begin with, then we can also make a conclusion that says phi or rho is true, and psi is no longer a part on the right hand side. So it's kind of cool either way, okay? So that's one ingredient, okay? That's one ingredient of what we need to understand. So now let's move on to the next ingredient. Okay, so we'll forget about that part here. We'll get the connection back to that thing. Let's be have a view of the overview of what I'm trying to say. So the next one is talking about CNF, conjunctive normal form. So conjunctive normal form is really just a fancy name, and I have a really kind of fancy way to define it. But at the end of the day, a conjunctive normal form basically means we have a big, long conjunction of stuff. Okay, the conjunction of what kind of stuff? Each thing inside a conjunction is a disjunction. So what is inside a disjunction? What can appear inside each disjunction is either a variable or the negation of a variable. Those are the rules. Okay, are we good so far? I can draw a picture, that may make it easier to understand. So we have a conjunction, a huge long conjunction. So the conjunction can have multiple items. Each item in the conjunction has to be a disjunction. What can be inside the disjunction? We have rules too, okay? Each thing inside the disjunction can either be a variable, PTRST, or the negation of a variable, not P, not Q, not R, not S, not T. Those are the rules. So it's a 3-tier kind of setup. The top tier has to be a conjunction, second tier has to be a disjunction, and then at the bottom level, it can only be a variable or the negation of a variable. That makes a CNF, a conjunctive normal form. Is that okay? All right, so if you are to write a syntax checker to see if an expression is a CNF, would you be able to do that? It shouldn't be too hard, right? Because it has a very distinct and restrictive format to it. So now here comes a claim, okay, which I will not prove until after the break. But today I want to give you kind of like an overview of what we will be talking about after the break. So the claim is, you can give me any Boolean expression, okay? It can be complex, can be very simple. I can always convert it into a CNF. Let me say that one more time. It's kind of magical, okay? You can give me expression, any Boolean expression you can imagine, using and, or, imply, equivalent to, and negation, okay? And you can structure it any way you want, okay? As long as it is syntactically correct, I can convert that into a CNF like this. So that claim by itself should be viewed kind of magical at this point because I haven't shown you how to do it. But the claim itself is pretty wild if you think about it, okay? Because I'm basically saying, look at this really restrictive way of making a Boolean expression. It has the same expressive power as every other Boolean expression. That is the claim. So are we okay with that claim and what a CNF is, what it looks like? Okay, so those are the two out of the three ingredients that I need. The third ingredient that I need is down here. It's called proof by contradiction. So proof by contradiction is actually a very powerful technique to prove theorems, not only in computer science, but also in mathematics in general. Have you guys taken the class where, there's at least one proof that uses your proof by contradiction? Okay, so some of you have exposure to proof by contradiction already. And which class would that be? Oh, okay. Yeah, proof by contradiction is deceptively powerful because it doesn't sound like much, but it really, really is useful. I can give you guys some examples later on. So proof by contradiction is the third component. So I have here, once again, a bunch of derivation. You're kind of using the same sort of stuff. So let's focus on just what is the result of this? What is true? Once again, to quote you a little bit earlier, it is the implication that is true. What is the big deal of this implication? This implication says, if I tell you that P implies Q is true, then I know this more complex implication also has to be true. It doesn't matter what R you're choosing, as long as I'm using a conjunction with R with P on one side, and I'm using the conjunction with R with Q on the other side, this implication is also guaranteed to be true. So that is a wild kind of conclusion, but it is provable because of all of these steps. So at least for now, we just have to say, okay, fine, your text says it's true, and it looks like it provided the proof as well. So we'll just say, okay, let's just say that it's true. What is the big deal? This by itself is not proof by contradiction. This is a corollary in order for us to prove that proof by contradiction itself makes sense. Look at this as a three-stage rocket, right? This is just the first stage. So the second says, okay, so if I say, psi implies phi is true, then what can I do? Well, I can now introduce not phi as R, and then I can now say, okay, so this implication here, where the cursor is basically using the corollary and introduce R as not phi. Okay, because there's no restriction of what you can use as the R. Okay, I can choose anything I want. So in this case, I decide I'm going to use not phi as my R. So you look at this and go, okay, so what is the big deal? So now we have psi and not phi. Okay, that by itself it doesn't seem very interesting. Implies phi and not phi. Oh, that one looks a little interesting because phi and not phi is guaranteed to be false. So that means in the end, I am basically saying psi and not phi is guaranteed to imply false. Okay, so wait, hold on a second here. If the implication is true, okay, this implication here is guaranteed to be true, but the right-hand side is known to be false already. So does that put a constraint on the left-hand side what it has to be? What do you think it has to be? It has to be false. Okay. In other words, if this implication is true, then when you make a conjunction out of psi and the negation of phi, this conjunction is guaranteed to be false. All right. So you go like, okay, that's a whole bunch of derivation. So what is the big deal of this? The big deal is a lot of times getting a direct path from psi to phi may not be easy. Okay, you might have to go. It may meander a whole lot. Okay, in order to get from here to here. But there's a shortcut sometimes. When you say, I'm just going to negate the theorem that I want to prove to begin with and make a conjunction with everything that is known to be true. And it turns out sometimes it is easy to prove that this conjunction is false. So that itself is proof by contradiction, which is a very, it's a term that is really kind of, it doesn't sound like what it is supposed to mean. Okay, yep.
And just to confirm, all of those implications
Mhm.
are true.
Correct. So let me say which ones are true. So we are given this implication is true to begin with. And then because of the corollary that we talked about earlier, this implication will also have to be true. But if this implication is also true, then this implication also has to be true. But if this implication is true, we have a constant false on the right-hand side, which means the left-hand side has no choice but to be false. Okay, so now we have the three main ingredients, okay? So what three ingredients are we talking about? Resolution, okay? What is the magical property of resolution? You start with things with three variables, we can cut it down to two. In other words, it is a way to get rid of stuff, okay? Things get simpler when you apply that rule, okay? Rule number, the second magical item, this is kind of like a fantasy, right? We're collecting these magical items in order to finish the quest. So the first magical item is resolution. The second one is CNF. CNF sounds really magical as well, because I claim that you can give me any valid, syntactically correct Boolean expression, and you can structure it any way you want, okay? And I'm claiming and say that, you know, I can turn it into CNF, which is a very, very restricted form of a Boolean expression. Okay, so that's the second one. And then the third magical item for this quest is proof by contradiction. So proof by contradiction means, you know, so in the context of what we're talking about here, this side here is the conjunction of everything in iota. Everything that is known to be true. Okay, this phi here is basically, you know, what we want to prove. Okay, it is the well-formed formula that we want to say, hey, that has to follow this. Okay, if everything in iota is true, this well-formed formula also has to be true. So phi is the theorem that we are trying to prove. Psi, on the other hand, is everything that is known to be true, that is given to be true. Is that okay? So most of the time, when we apply propositional logic, that's what we want to do. We want to make that connection, okay? A chain of implications, okay? But this says that, oh, sometimes you don't need that chain of implication. All you need to do is to combine everything that is known to be true and the negation, this is important, the negation of the theorem that you want to prove. If that conjunction, if you can prove that conjunction to be false, then you have just proven that the theorem is true if everything in the iota is true. Is that okay? So these are the three magical items that we have collected for the quest, okay? So the actual quest, we'll talk about it after the break, okay? But the overall art is this, okay? So now let's get back to, we have enough time to talk about proof by contradiction. So we'll go ahead and see if we can use proof by contradiction to prove things that are otherwise difficult to prove directly, okay? And I have at least two examples. The first one is well known because it is known as the pigeonhole principle. So what is the pigeonhole principle? Does anyone know what is the pigeonhole principle? Okay, I believe it is somewhere in here too. So let me look for pigeon. There we go. So as an exercise, we are looking into the pigeonhole principle. And let me get rid of the search so it doesn't highlight anything. So the pigeonhole principle states that given n pigeons and m pigeonholes, and we have more pigeons than there are pigeonholes. And when all the pigeons come home, in the evening, then we have at least one pigeonhole having more than one pigeon. It makes sense, right? It just intuitively makes sense. But can you prove that this has to be the case? In other words, you can also look at this as cars and commuting, right? So you have more people, more commuters than there are cars. And then the idea is, if everyone is commuting properly and no one is sick and staying home, then at least one car has more than one person. It seems to make sense, right? There are more people than there are cars, and it kind of makes sense that at least one car has more than one person. Now, can we have one person driving a school bus and everybody's on that bus? Sure. But doesn't that also tell you that that bus has a lot of people, more than one, right? But how do you prove it? How do you prove this has to be the case? So you use proof by contradiction, okay? What does it mean? So proof by contradiction, the first thing you need to do with proof by contradiction is to identify what exactly is the theorem. What is it that you're trying to prove? So that's the important part. You have to isolate that part first. So in this case, okay, we need to negate the theorem first. But what theorem are we talking about? So the theorem is basically saying at least one pigeonhole has more than one pigeon. That is the theorem. That's what we want to prove. So what happens when you negate it? When you negate this, it basically says it is not the case that at least one pigeonhole has more than one pigeon, which means, what is the other way to say this? What is a more convenient way to say the negated version of this?
No pigeon has had more than one.
Exactly. No pigeonhole has more than one pigeon in it. So that becomes the negated theorem. So now we want to combine the premise, which is we have more pigeons than there are pigeonholes, and the negated theorem, which is all pigeonholes have at the most one pigeon in it. Okay, and we combine those two and see what happens. So you go like, okay, so we have m pigeonholes, and since each pigeonhole can only have up to one pigeon, so the total number of pigeons will be m. Okay, and we know there are n pigeons to begin with, because that's the premise. That is not part of the theorem, that is the premise. And now how do we relate those two? Okay, so I actually get it down here. Well, I use injective and surjective, but it's not even needed to do that, right? So we have, so one way of looking at this, we end up with at the most m pigeons. Okay, the number of pigeons has to be less than m. In other words, n has to be less than or equal to m, right? That's from derivation. But the premise says n is greater than m. So now we have these two conditions. The premise, which is what we know as psi earlier, says n is greater than m. And then the derivation using reasoning, using the negated theorem, ends up telling us that n has to be less than or equal to m. Can those two be true at the same time? They cannot. So when we look at the conjunction of those two, okay, let me just kind of write out the conjunction here. N is greater than m is given. But what we can derive from the negated theorem is n has to be less than or equal to m, because each pigeonhole can only have up to one pigeon. So the number of pigeons can only be up to the number of pigeonholes. So when you look at this conjunction here, it is false. This entire thing is false. So that is the proof, okay? It is using the principle of proof by contradiction to show that the pigeonhole principle is sound. It is correct. Is that okay? I can give you another one. And this one involves socks, okay? So the idea is I only have, okay, I would say, 3 different types of socks in my drawer, okay? Okay, let me see if that works. Okay, we'll make it really simple. and say that I only have one type of sock in my drawer. And I want to prove that, well, actually we can have more socks, but I think one type is fine. So I only have one type of socks in my drawer. So this way, every morning I just have to reach into the drawer and just pick 2 socks, and I guarantee to have a match. Well, can you prove that that is the case? Now, if you think this one is not interesting, then we can say, what if tag has 2 different types of socks? And every morning I will reach into the drawer and I'll take 3 socks out. And out of the 3 socks, I can guarantee that there's at least 1 pair. It will match. But how do you prove it? So a direct proof is actually difficult in this case, but an indirect proof or a proof by contradiction is easy. Because what is the theorem? The theorem is if I pick 3 socks out of my drawer by random, I guarantee to have a pair. In other words, 2 out of the 3 would be the same, right? So you negate it and basically say, okay, 2 out of 3, you cannot find a pair of the 3. So that means all 3 have to be different. But now it is contradicting with the premise, which basically says, I only have 2 different types of socks. And you come to the conclusion that I have 3 different types of socks. So it's a contradiction. So once again, I'm using proof by contradiction to prove something that is very much intuitive. You just go like, it makes sense. But if I ask you to prove it on paper, it is really difficult to prove. But proof by contradiction makes it a snap. Are we understanding proof by contradiction a little bit more? Okay. So you cannot remember how, the context of the introduction of proof by contradiction?
I was wondering that it's kind of like, prove that like all powers of 3 are odd or something, contradiction.
Oh, okay. That sounds like it would be a good application of proof by induction as well.
Yeah, so they were all like approved to that induction.
We will get to proof by induction in this class too, because it's a very important technique to prove. So what I'll do next, okay, this is something that you can try to do over the break. It is a little bit more difficult. So I want to show that, I want to know whether a number is prime or not. Okay, so let's just say that's what I want to do. I want to write an algorithm to find prime numbers. Okay, that doesn't sound too hard, right? So what I'll do is I'm going to use Joplin to kind of write down some examples here. All right, so I want to show, I'm just randomly going to pick a number, 157, okay? I don't even know whether it's a prime number or not. So the question is, when do I stop? So I look at, 157, and, I'm not particularly smart. So the first thing I do is, let's mod 2. And you guys are go like, oh, but tech is easy because, the least significant digit is by itself a odd number. It cannot be a multiple of 2. Let's just say I don't know that rule, okay? So I look at this and go like, okay, that's a 1. And so 2 is not a factor of 157. Okay, so then I try the next one up. Okay, 157 mod 3. Let's see, we got, it actually also has a remainder of 1. So it is not a multiple of 3. So at this point, I cannot find a factor, but I cannot yet confirm that 157 is a prime number, right? So let's just say that I'm really not that smart and I'm gonna go like this, okay? I'll try 4. So if you look at this and go like, let's see. So if it's 4, we have 37 divided by as a remainder of 1, I think. Okay, and then we have 157 mod 5, and that has a remainder of 2. 157 mod 6 is 1, I think, and so on. So the question is, when can I stop? So I'm going to switch gear to use a spreadsheet because doing this by hand is not the best use of time. So I'm going to use a spreadsheet here. spreadsheets are very useful, in this class and also in CISP440. I make use of spreadsheet a lot because it's really just a fancy calculator. Okay. So we have 157 as the number that we are checking. I want it to have its own cell so I can change it and do things later on. So we want to find out, what is the mod of this and the row number of this row. And row number is basically 2 in this case. So I'm using the row number as the potential factor just to make it a little bit easier to deal with. And I also need a $sign here because I need it to be absolute because otherwise I cannot copy and paste. So I'm going to copy and paste a bunch of times here. So now we have shown up to 11, 12, and 13, and I can stop here. Right here, okay? Once I confirm that 13 is not a factor of 157, I know 157 is a prime number. Yep. So say again? Why specifically 13? Aha, because if I express 157 as a product, okay, so let's say 157 is A times B, okay? One of those two, okay? A is less than or equal to the square root of 157, or B is less than or equal to the square root of 157. So once I have tested all the way up to the square root of 157, which is a little bit less than 13, once I confirm that 13 itself is not a factor of 157, I'm done. So the theorem is basically just saying, if you have a product of 2 integers, okay, so let's say natural numbers, okay, non-zero natural numbers. So let's say you have A times B equals to C, okay? Then I guarantee you that A is less than or equal to the square root of C, or B is less than or equal to the square root of C. That's the theorem. How do you prove it? Let me write it on the whiteboard, okay? Because this is something that you can do over the break. Because I know some of you are traveling, okay? You're taking the plane, so you've got nothing else to do when you're just at the airport. So when you got nothing to do, you just look at this thing here and go like, how do we prove it using proof by contradiction? So I'm saying that if C equals to A times B, okay, we're talking about non-zero natural numbers, okay? Counting numbers. If this is the case, it implies that A is less than or equal to the square root of C, or B is less than or equal to the square root of C. This theorem is what allows me to stop at 13. Because if there was a factor, I would have found it already. So this is the theorem, okay? If you want to be a little bit more complete, you can always specify, A is greater than or equal to 1, B is greater than or equal to 1, okay? Which I don't think is really necessary, but we can just throw that in. Okay, so given that A, B, C are all integers, A is greater than or equal to 1, B is greater than or equal to 1, how can we establish that A has to be less than or equal to C, the square root of C, and B has to be less than or equal to the square root of C? So this is a little exercise over the break. Sorry? Next week is spring break. And that's why the gas prices is up already. Yep, so we do not have class the entire next week. I'll see you guys the Monday after next week. All right, well, enjoy your spring break, but try to work on this proof as you are spending time at the airport. You can even use ChatGPT. This is a good idea to kind of try out ChatGPT and see if you can formulate the question in a way that ChatGPT can understand, and they can check whether it is giving you the right answer or not. Yes.